So I don't see anyone wandering in anymore, so I think we'll just get started. I'd like to introduce Jonathan Yeung. Jonathan has worked at Spartan Controls for over 17 years as a measurement resource, starting with 9 years as an application engineer, and the rest of his time as a technical specialist, visiting customers across BC and Alberta to help support their measurement needs. In his spare time, Jonathan loves spending time in his garage and driving his car on racetracks. So please welcome Jonathan.
Hello, can you guys hear me? Okay, perfect. Thanks for coming in. I was not expecting this room to be quite this expansive. So thanks for coming in and attending this talk. All the cool people sitting in the back. Okay, so as mentioned, my name is Jonathan Yeung. I'm the measurement technical specialist at Spartan Controls, which is kind of a bunch of very generic words thrown together. But I specialize in instrumentation specifically. And I cover a lot of different industries, water and wastewater being one of them. So just a quick bit of background of Spartan Controls in case you guys weren't aware. We are, I guess, an industrial automation company, and we support industries all across Western Canada. So that's BC, Alberta, and Saskatchewan. We have a lot of different offices scattered throughout those areas, and we cover a lot of different industries. So myself, I work closely with a number of different people on our team. And so we kind of cover different industries in different ways. So I focus more on the instrumentation side. I work closely with my colleague Jim Yargeau, who some of you guys might know. He's an account manager that works closely with you guys. And so he's got a big focus on water and wastewater. And I focus quite a bit on the instrumentation side, covering all the industries in my territory. So we've been around for over 60 years. For those of you who are trying to answer the little quiz question, that information was slightly out of date, but basically we're still at 60 years, 60 plus. And what we do, like I said, is we do a lot of industrial automation. So that could be anything from plant automation, a lot of electrical related stuff with VFDs. We got a guy back there, Tom, who knows quite a bit about it. And we got valves and actuation. I think a lot of people know Spartan for valves, but I'm here specifically to talk about measurement instrumentation. But we also get into reliability equipment. So on our demo booth, sort of in the back corner there, we got a couple of demos you can take a look at. And we also do some sort of custom packages included. So obviously today we're here to talk about instrumentation. And specifically we're here to talk about non-intrusive flow measurement. So has anyone, just show of hands, has anyone heard of or worked closely with non-intrusive or clamp-on ultrasonics specifically? Okay, so there's some familiarity around that. So the company that we represent is a company called Flexum. So we, for the most part, represent Emerson Process Management. And Emerson acquired Flexum late last year. And so Flexum's a company based out of Germany. And so they are quite German about a lot of things, which in many ways is really good. Sense of humor is probably not to my taste, but they have a good product. And we've been very pleasantly surprised with the stuff we've had so far. So quick agenda. We're going to talk about a little bit of the fundamentals, just because I think it helps explain, put a little bit of context to what we're trying to cover and why we do things a certain way. We're going to talk a little bit about installation best practices, and hopefully if we have time at the end, I can kind of show you how we typically set one up. We're going to go through some application examples, because I think that's really important to show that we have these things installed, what are some things to kind of watch out for, and some lessons that we've learned from it, and also some measurement options at site, because sometimes it's not, the nice thing about non-intrusive flow measurement is that you can kind of put it onto a location, move it to a different location, or you can use it as a test base, and we'll talk about some of the options we can have in those situations. Okay, quickly about theory. I'm not going to spend too much time here. Basically, the main advantage of a clamp-on ultrasonic is high flexibility. So what this means is we don't really care about what's in the pipe. We don't really care about what your pipe material is made out of. We don't really care about your line size. A lot of those things we can really accommodate and accomplish because we don't need to have any pipe changes, right? So that's another big advantage. So if you, say, want to add a flow measurement to a location that previously didn't have it, if you want to add something like a magnetic flow meter, you would have to cut the pipe, make some pipe changes, add the mag in, and we don't really have those limitations with clamp-on ultrasonic. Accuracy's decent, I would say. So we're typically sitting about 1%. We can do volume, mass, and concentration if we need those things. The maintenance is quite minimal. We don't have to worry about erosion or corrosion unless your pipe is literally bursting. Then we got probably other issues. And then, of course, we have, like I said, a lot of flexibility around piping. So you don't really have to make a bunch of changes. We can just use what we have. So a couple examples. A lot of common questions is how far down can we go, how small of a line size. So we can go down to a 1/4-inch tube, which I think is quite small for most applications, all the way up to 22-foot penstocks. That's basically a horizontal tank. And the only thing we change is the transducer. So obviously, the larger the pipe size, the more sound we're going to have to inject into the pipe. So we'll just need bigger transducers. And then the fan favorite here is a picture of some old wooden pipe. So yes, we can actually have a clamp-on ultrasonic work with wooden pipe. So that's just an example of some of the flexibility we can get. Again, like it doesn't really matter what the piping material is. Okay, it's not all sunshine and rainbows, and I'm not here to tell you it works in every situation. So one thing is if you want accuracy for, say, custody transfer applications, clamp-on ultrasonic's not really the technology. Okay, that's what magnetic flow meters are probably better suited for. Not that you guys have this, but if you have any sort of steam type applications, that would be a limitation. If you have a lot of solids, and I'm talking about it's probably more solid than liquid, then we can run into some issues there with clamp-on ultrasonics. And anytime the pipe is not uniform. So what that means is if we have a pipe that's ribbed, it becomes very difficult to put transducers on, or if the pipe has a lining in it, we can't always be sure that the lining is uniform all the way through and also doesn't have an air gap between the liner and the pipe. Okay, so those are kind of the limitations there. So what are we trying to look for? What we're trying to do is, for this flow meter is anytime we need a temporary measurement, this is a great application for that. You just want to get an idea of what's happening in a particular line. If you have a flow meter you don't trust, here's another option we can put on just to verify it. So there's an example of a clamp-on ultrasonic compared to a magnetic flow meter. The output's quite close, so we know we have a lot of faith in the magnetic flow meter. Or if we have like a situation where downtime is just not an option, we can quickly throw a meter on there. The picture on the bottom right is an example of where a flow meter had delivery delays. Not that we have ever heard of that in the last 5 years. But we can quickly throw one of these on, get a flow measurement until that more permanent measurement shows up. Another one that we've run into recently is if you guys have had confined space locations or you guys have had an old flow meter, like you did at City of New West, then it becomes very cost prohibitive to take that meg meter out of line. We can put one on quite easily onto that line. The other one is another example we ran into recently is also a municipality we spoke to. They have maybe a lack of flow measurements out in the field, and they think that there's a leak somewhere, and that flow measurement, that flow is going somewhere, and they're not quite sure. Well, then this measurement gives us a lot of options in terms of putting one on and fine-tuning exactly where that leak is happening. So basically, just a lot of flexible reasons. We're essentially only limited by our imagination for clamp-on ultrasonic, but of course we want to be aware of the limitations of the technology. Okay, very quickly, how does it work? I'm going to use some boats. I don't know if there's any boating people here, but basically we're going to use this as an analogy for how ultrasonics work. So if I have a dock on the left and a dock on the right, and I try to get a boat from left to right and right to left, under normal conditions, the two boats will take an equal amount of time to go back and forth, right? So pretty straightforward stuff. Now, if I have a situation where the river is flowing left to right or the water body is flowing left to right, obviously the boat on the left is going to go much faster. It's going to reach its destination much more quickly than the boat going right to left, right? So that essentially is the transit time method, and that's what we use for ultrasonics. Okay, someone got a little carried away with the animation here, but I think you guys get the gist of the point of this example. And so for non-boating applications, what we do is we use ultrasonics to the same degree. So we have a transducer. It sends a signal to another transducer, and it could be on the same side of the pipe, or it could be on opposite sides of pipe. But the point is that the movement with the flow is going to be a lot quicker than the movement against the flow. So we kind of plug that into an equation, and we're able to work out the velocity inside the pipe. So very quickly, we have a couple different technologies for getting that measurement. Shear wave is what we typically use to kind of calculate that time difference. But there's also another technology called Lamb wave, which we use on maybe aerated flows or anything that could be potentially noisy. It's just another option, slightly less accurate, but just know that, again, we have more flexibility there. So we can measure in all sorts of different applications. We can also get concentration measurement. Okay, so what we do is we look at the speed of sound, and the speed of sound is directly correlated to a concentration value. We also need to build a table to tell us that. But between concentration and temperature, we can also work out density of the product if that interests you. So again, a lot of different options for this measurement. So another common question I typically get is, what kind of accuracy can we expect from a clamp-on ultrasonic? Now, the number that we typically go by is 1%. The 1% has some caveats to it. So if the piping is non-uniform, if we say have fiberglass pipe and the thickness is not consistent all the way, well, then that's going to affect the accuracy. But generally speaking, we'll do a sizing to know what that number is, and we can get pretty close to 1%. And that will, a piece of information we'll provide to you. So how do we get that 1% with a clamp-on ultrasonic meter? Well, we do factory calibrated pairs. So those two transducers are matched together. But the key differentiator here is that there's a temperature sensor built into that piezoelectric crystal. So that's what gives us direct temperature compensation. A lot of clamp-on ultrasonics on the market will utilize a temperature sensor outside of the transducer, and that may not be representative of the temperature that the transducer is actually seeing. And those are the temperature effects we want to compensate for. Okay. This is a bit of an eye chart. Basically, the main bits of information that we want to collect for understanding whether this is a good fit or not is line size, line material, pipe thickness, and basically a bunch of like your process details. Okay. So the more you can give us, the better. There's some other things in here that could be really beneficial, like understanding, what power you have available, what are your piping disturbances upstream and downstream are. Those are nice to have, but at the end of the day, to spec one out, to understand what sort of accuracy we can get and whether it's going to work for the application, those are the key details. Okay. So a quick example, and again, a bit of a chart. This is a 20-inch water pipe. So we have a flow rate of 0 to 500 cubic meters per hour, and this is sort of what we would typically do for the sizing. So you'll see, it's, again, a lot of things to look at, but you'll see here that we have a bunch of transducers here that get listed, and then from there we decide which ones are a good fit. And then we also look at what you see, that SP number is, tells us how many paths. So an SP equals to 1 is one sound path. So that means the transducers are opposite on opposite sides of the pipe. If we have an SP of 2, then we're doing a bounce path. So there's 2 paths. It's technically 1, but anyway, this is the German North American part. But yeah, so they call that a 2-path. And what that number underneath tells us is how far apart the transducer should be mounted. So this is why the sizing is really important, because that tells us exactly where we should be mounting the transducers. And we don't want to just throw it on there willy-nilly. And if we get time, if I stop talking, then I'll show you what I mean by that. And then this is sort of the accuracy chart that we would be talking about. So if you look at the top left-hand corner, you'll see kind of across a range of different flow rates. For this particular application, we're looking at about 1%. Now you'll see a number there that says around 7%. That's 1/10 of the flow rate that we were originally given. So that number is fairly low. And you can see sort of the accuracy graph down below, so you can get a rough idea of where we are on that accuracy curve. Okay, installation best practices. So this is kind of key. So on all of our transducers, we have sort of an arrow that kind of points together. And when we talk about the separation distance, we're talking about the face-to-face between those transducers. And typically, we want the transducers to be mounted in a way that they never get interfered with. So if there's any potential for error in your pipe, any sedimentation on the bottom, then we typically don't want those transducers mounted at the top of the bottom. So we want them to be on the side. And of course, we want the pipe to be full as much as possible. So this is why we have, obviously, ideally, a vertical up orientation. And we typically don't want the product to be falling through the transducers. And we don't want them to be at high points, because that's where you can start to have pipe that isn't full. Okay, so a couple of things around mechanical installation. So we have, for those of you who've been familiar with non-contacting clamp-on ultrasonics, typically you'll apply a gel to the pipe and then stick that on. But over time, what can happen is the gel can evaporate, wash away, whatever. So on our permanent transducers, what we do is we apply a coupling pad. And then we have an algorithm built in that can actually compensate for the coupling pad, so we don't get a loss in accuracy there. And that way, there's very little to no maintenance on the transducers. You can kind of stick them on, and they're on for good. Another thing is mounting options. Okay, so ideally, if we have enough piping, what we would do is we would put on this bracket. And the bracket has a scale on there, so you can quickly and accurately make sure the transducers are lined up, and you know exactly the place you've mounted it is as per the sizing. There's also a more covered option that's really good for submerged or buried applications. And then sort of the most flexible option is to use straps, okay, that we can kind of put them on anywhere. They're a little bit more tricky to get on, of course, but that is another option. Okay. So straight piping is another one. Now, all these numbers I show here are to get that 1% accuracy. Okay, so for a 90-degree bend or any sort of reducer, we typically want 10 diameters up and 3 diameters down. If we have a pump, that's going to introduce a lot of turbulence to the system. So we typically want 20 diameters upstream. If we have a double elbow out of plane or a valve, then we need up to 40 diameters and 3 diameters down. Now, that sounds like a lot, and it is, but that's for accuracy. So if we are talking about repeatability, if you just want a repeatable number, we can get that without meeting those straight pipe diameters. Exception to that, of course, is if you have a dynamic disturbance upstream like a control valve or a pump on a VFD. Those are obviously exceptions. But if you just have an elbow or you have a expansion or a contraction or whatever it is, then we can get 1% repeatability pretty much across the board. Now, there is something called a software feature on Flexim units called disturbance correction. And basically what this is in Germany at the National Metrology Institute, they did a whole bunch of testing with a whole bunch of pipe disturbances. So we have a bunch of empirical data that says, hey, if we do not install this as per the straight piping requirements, we are still going to get X accuracy, which will be significantly better than what it would be out of the box. So this is an example of what it would look like. So here's the sizing we did. So if we had perfect 10D, 3D upstream, downstream diameters, we would be looking at around 1%. But let's say we actually don't have that 10D upstream. Let's say we only have 6 inches before an elbow. Now, I can actually, if you look at the accuracy there, we're about 3%. So 3%, 6 inches away from an elbow is pretty good, in my opinion. So this is an example of that disturbance correction and how it can really help us through some of these trickier applications. Now, obviously, that testing was not done with every single pipe disturbance known to man. It was done with the most common ones. So of course, we're not going to be able to accommodate every situation, but we do have a lot of we do have another option here if we can't get that straight piping. Okay, so I've sort of already covered this. I don't want to spend too much time on it, but if we want to improve accuracy above that 1%, there's a couple different ways we can accomplish that. We can add more transducers, which sounds like a pretty over-the-top solution. But if you have pipe disturbances that you just can't get around and that disturbance correction is not an option for whatever reason, then we can add more transducers to the system. Obviously, that's going to add cost. Okay, so I just want to make sure you're mindful of that, but just know that there is another option there. Another question we get often is, I mean, you guys work in industries where the areas where flow meters are can be submerged quite often. So what is the IP68 rating of the transducer? So we've had extended IP68 testing where we can handle 20 meters of submergence for 90 days. Now, that doesn't mean that at 90 days, the transducers will just stop working. That's just the duration of the test that we were able to get with IP68. So we have a lot of transducers out in the field who have been submerged for years, and they still work. But we have to make sure we select the right options and that we provide a proper shield for the transducers, and they'll work for those applications. Okay, but we just don't have that on a certificate. So not going to spend too much time on this, but basically this is the procedure for setting one up. We're essentially just wanting to input what the pipe material, pipe thickness, that kind of stuff is into the system. And then we configure the transmitter for the number of sound paths we're putting in. And then we check a couple of diagnostics to make sure that it's looking OK. So a couple of those diagnostics is signal to noise ratio. We want that number to be over 10. And then there's a signal to correlated noise ratio. We want that to be somewhere between 25 and 50. And then we just want to make sure the speed of sound is somewhere in the ballpark of 1,400 meters per second. OK, so a couple of keys to installation success. We want to make sure that we do a review of the application. We don't want to go in cold necessarily. We want to understand what your piping and your flow conditions are. If you're still unsure, we can also do something called a field test, where someone like myself or a service technician would bring a portable unit out to your desired application, and we would just make sure it works. So there's a couple of things. We can also loan you guys a unit. So there's a rental program we have. So that's another option. We can offer commissioning assistance if this is the first time you've worked with clamp-on ultrasonics, or if you've previously had a bad experience with clamp-on ultrasonics. I think training is also very crucial, so just making sure you know the ins and outs of how the stuff works and what all the different options mean. And then, of course, another sort of next level would be something called online monitoring, where we hook up a LTE gateway to it, and we can beam all the information remotely, so you can see all the information from it. OK, someone had a lot of fun putting Lego presentations together, so thanks, Jimmy. So the online monitoring is obviously going to use the cloud, and that was just sort of an excuse to put that in there. OK. So when we do commissioning, what we do is we do an installation verification. So those are some of the diagnostics I talk about. And then we take a look at the sound signal coming from it. So we get this like little sound wave. And what we're looking for is we're making sure that the signal before and after are relatively clean. Okay. I'm not a sound technician. I can't speak too much more beyond that about this stuff. But we just want two signals to go back and forth. So we see a blue line and a red line. So we know we're getting sensor one way and another way going back. And we want that signal to be relatively identifiable, which it is in this case. You guys ever have to kind of check your meters and make sure they're working correctly? Anyone? How do you know your meter's working correctly? I guess it's kind of a rhetorical question, but obviously we can send a service technician out to diagnose some of that information. But there's also a diagnostic feature called advanced meter verification. So essentially what we're doing is we're automating what the service technician would do and would output a printable report. So really good for our audit trail. So if you guys really love paperwork, this is one way we can add paperwork to the system. And basically, I think the one advantage to this, one of many, is that not only is it an ISO document, So it's not just some random document someone put together, but it also gives you guidance on what to do and also gives you a trend on how things are going. So if something is deteriorating, it's probably hard to see in the picture, but you can see the trend. There's like a up or down arrow. So if you've had installed for a long enough period of time, you've run enough times, you'll get a trend on how that is going. So you know what sort of corrective actions to do. This is an example of what the report looks like in a bit more detail. I'm sorry, it's just a couple of screenshots. But essentially, it'll show you, probably should have whited out that end username, sorry about that. But it'll show you what the application is. It'll show you all the diagnostic variables, and it'll basically tell you whether it's good or not. Now, obviously, this was a one-time deal, so we don't have a trend on this particular document. But on a permanent installation, if you guys used it a number of times, you would get that, okay? People who like to read a lot of content, there's also a methodology page on the back. So if someone says, well, I don't believe what that says, or I don't know where all that stuff comes from, there's a whole bunch of information on the back and an explanation of a bunch of 3- and 4-letter acronyms, which I personally really appreciate. I'm worried that my kid, when she gets older, will not know what KFC stands for. So having a document like that will be really beneficial. Those jokes are going as well as they normally do, so thanks for laughing. So another option we can have is something called Empower. So this is sort of the cloud GIF I had earlier. So we can beam all this information to a cloud and have you guys access this information. So if you guys have an installation which is in a remote location, we can quickly look at the diagnostic variables and tell you immediately whether this meter is okay or not. So this is another option that you can have. Okay, applications. Obviously for you guys, we're primarily focused on liquid applications. So like I said, wide range of applications we can handle. There's essentially no restriction to pressure at all. And temperature, I mean, that's going to be beyond what you guys are going to see. Velocity, we can go from 0.01 meters per second all the way to 225 meters per second. That's quite a big range. And then, of course, two-phase limits can be a bit tricky for clamp-on ultrasonics, so we don't want more than 10% void fraction. Okay, so this is an application that we did with City of New West. And so this was they had an inline mag flow meter that was installed for 23 years, and it had not been working for quite a while. So it was actually buried under a piece of road, and there was only a manhole cover to get in. So getting the magnetic flow meter out was quite tricky and quite a difficult thing. So the other part to it is that this chamber had actually flooded several times. So again, as you can imagine, getting a new meter would be quite troublesome. We would actually have to dig up the ground to get access to the mag and drag it out. So that would involve shutting the road down, quite a lot of work. Now previously, the customer had tried a different clamp-on ultrasonic and got a variation reading of 7.5 to 17%. So they were feeling a little bit, I guess, worried about how reliable this measurement would be. So you can see we started installing it. We went to site. There's a bad angle of me over there. But we essentially installed the transducers on the side of the pipe, and we had a decent amount of straight piping, and then we wired up the transmitter box about 50 feet away, and we were able to get a pretty good reading out of it. So the results, the meter was installed in about 6 hours. That's total start to finish, including all the mechanical and electrical installation. We didn't have to dig up any of the road. The mag was left in place just as a spool piece because it was already there. No need to disrupt it. And the cost of the mag, the cost of the clamp-on ultrasonic was roughly less than 60% of what a new mag would be. So at the end, we estimated that the cost savings were about $50,000 for that particular installation. We didn't have to shut the line down. We didn't have to depressurize. We didn't have to do any hot tap welding. We didn't have to modify the chamber. We didn't have to dig up the road. We didn't have to shut the road down. Okay, we basically coned it off for a few hours, and then we were done. This is probably a trickier application, and maybe shows an example of something a little bit more extreme, where we had a fiberglass pipe, And this is on an acid flow application. So this was, customer told us it was 35% hydrochloric acid. They gave us a bunch of flow rates and told us some process details, which sounded a bit sketchy. So I did a sizing, and it looked like we were kind of on the bottom end of the accuracy curve. So we were saying to the customer, wow, that really doesn't project very well. But just know that the accuracy was definitely on the lower end of the scale. So you can see on this curve here, like this is that red zone. We're kind of on the bottom end of that flow meter. So not the greatest install, but the customer wasn't able to shut that line down, and they just want to see if this clamp-on ultrasonic would work for them. So we then looked at and said, well, if we added more transducers, can we get a notable step up in accuracy? And for this particular installation, it only improved the accuracy by about 1% or so. So in that particular installation, it didn't make sense to add another set of transducers and incur that additional cost. So we get to site, and the customer's like, oh, actually, you remember those flow conditions I told you? Those were all wrong, so here are the new flow conditions. And the nice thing is, because those flow conditions were quite a bit of a step up from what he originally gave us, it actually turned out to be a better fit. But the concentration of hydrochloric acid was also different. So if you look at the speed of sound charts, you'll actually see the speed of sound is different between 36% HCl and 35% HCl. Probably a lot more than I would have expected. So we do another calculation, and this one looks a lot better. Okay, so we're happy with that. We're excited. Now, the one thing that kind of threw us off is when we asked the customer what the FRP pipe thickness was, he told us 9.4 millimeters. I have no idea what that number is because I don't understand small metric values. But he made it sound like it was very consistent. And when we went to measure the thickness, it varied from 30 thou to 80 thou of an inch. So that can make it very difficult for a clamp-on ultrasonic meter, because obviously we're now talking about different thicknesses that sound wave has to move through. Okay, so in this particular installation, we took a look at to see if, again, we're now looking at accuracies of around 1%. Down at the bottom, we would be somewhere in the 6% range, but for most of their flow rates, they were sitting around 1%. We looked to see if multiple transducers, again, would improve that, but not in an appreciable way. So we decided to kind of skip that as an option. Okay, so that's sort of just one example. We have a number of clamp-on ultrasonics installed at a number of different municipalities and different industries as well too, but here's a quick snapshot. Okay, so quick summary. Accuracy, we're typically at around 1%. We have a lot of different options for improving our accuracy for different installations. Submergence, we can handle up to 20 meters for up to 90 days, according to IP68. It's non-intrusive, so all the flexibility that we gain with those installations. And then, of course, we have an audit trail and the ability to diagnose whether the meter is good health-wise or not. Okay, so we're going to try to do a demo. And we have a camera guy coming up. So I'm going to get off this very distracting GIF. And good to know there's like 2 people laughing. That's 2 people awake. Okay, so before we switch to questions, this is basically an example of a clamp-on ultrasonic that we would typically have. This is our portable unit. And so in these situations, geez, I don't know if you're going to be able to see that here. Can you see that? It's probably a bit dark. Oh yeah, that's great quality, guys. Sorry. Better. How about this way? Is that better? Okay, can you sort of see what that says? Okay, so basically we have this is an example of a typical installation. So we got a 3-inch pipe, we have a transducer, and I've just sort of pre-mounted this like you see in those cooking shows where all the prep work is sort of half done. But basically what we would typically do is we'd want to understand what the thickness of the pipe is. So I would hook up included with our portable unit is one of these guys, which tells us what our thickness is. So I would just put this onto the pipe at various locations, and it would tell me, assuming this all works as planned, it would tell me typically what the pipe thickness would be. Okay, this is going well. So I forgot I actually have to go and make a bunch of these parameter changes. So the pipe material in this case is stainless steel. Temperature is 15, although it feels like it's rising because I'm getting worried about this. Okay, so we're going to try measuring this time. And so it's telling me that it's about 0.1 inch thick. I don't know if you guys can see that. And then typically what I'll do is I'll measure it at a couple different points. Obviously, I need a bit of this dielectric gel to test different locations. So yeah, we're pretty much at 0.1. Okay. So with that done, now what I can do is I can configure this for the actual transducer measurement. So I will plug in my transducer line, which is over here. Okay, still got 10 minutes. So it says clamp on detected. We're going to go through and set this up. Parameter channel A. So I went ahead and measured this diameter. You're just going to have to trust me that a 3-inch pipe is roughly 11 inches. Okay, I'm not making it up. The wall thickness, we said it was around 0.1, so 0.11, pretty close. The pipe material is stainless steel. How's that?
No, that's better.
Is that way better? Okay. There's no lining in this particular installation. And we're just going to assume roughness. It's a pretty smooth pipe, so I'm not going to add anything in there. The medium in this case is water. Medium temperature is 15 degrees. We're just going to assume it's pressurized to 55. And then what I'm going to do is going to go to the measuring portion. It's on channel A. Measuring point number, yes. There's 2 paths because we're going to do a bounce path, so have it on the same side of the pipe. And then it's telling me that my transducers need to be roughly 6.5 inches apart. Okay, so what I'm going to do is I'm going to measure roughly 6.5 inches. So I know I'm roughly about there. Okay, and then what I'm going to do is I'm going to apply a bit of gel to this guy here. And if this is not too tangled up. This is where it'd be nice to have like that overhead camera view, like they have on those cooking shows. Okay, so I'm going to roughly line this up. And it doesn't have to be perfect the first time. Okay, I'm going to tie the chain around. And then I'm going to tighten this guy up. And again, the key thing here is making sure that the arrow, the back of the arrow kind of lines up with the front of the arrow, roughly. Now, obviously, I would do this in such a way that I would be more advantageous for me next time. Okay, so I have that. I'm just going to do a quick double check, make sure that's roughly 6.5 inches or 6.42. Okay, we're a little bit out, so I'm going to shift that. Okay, to that spot. And again, just a quick check. Okay, we're pretty much bang on 6 7/16. Okay, so then I'm going to say okay. And so what I'm looking for here is there's like an S number, and there's a number of different diagnostics I can show here. So the S number kind of gives me sort of an idea of the signal. And then we have down here, this is the Q value. So the Q value is kind of an indication of the quality of the signal. So right now it's quite low. So I can actually sort of move this around until that number, you see how that changed instantly? So ideally the Q number would be almost kind of maxed out, but just for the purposes of this demo, you can sort of like shift the transducer around and see, okay, what makes the most sense until I get a number that I'm happy with. Oh, it looks like I had a better number earlier. Anyway, I think you guys get sort of the idea. So I would just sort of play around with that position until I get the value that I'm happy with. And then I would, okay, so the Q numbers jumped all the way up, so I'm looking pretty good there. And it says my transducer's distance is actually 6.425, so I almost nailed that distance. So thank you. That was, and then what I would do at this point is I'm pretty much done. So I would just wait, send online. So it would tell me a volumetric flow. Now, obviously, we don't have anything flowing, so it's not going to show anything, but this is typically where we would get a volumetric flow rate out. And this is essentially how you set one up. So as you can imagine, it's not, like I just did this on a table in the middle of a conference room. Obviously, in the field, it's going to be a little bit different, but I think from that, you get sort of a general idea of how you set one of these up, and it's really pretty straightforward. Okay, I'm going to open it up for questions.
I already have one from online, and it starts with, nice presentation. Then it says, the thickness of the pipe, viscosity, and temperature in the pipe can influence the reading accuracy? Question mark?
Short answer is yes. So all of that plays into kind of like how much momentum the fluid has, or sometimes we'll refer to that as like Reynolds number, and so that will be really important for the when we do a sizing. So ideally, we would have some of those values. Now, if we're just talking about water, we can kind of pretty accurately understand what a viscosity of typical water is, or if you guys have an idea of what the solids number is, we can kind of estimate it. But yeah, that would have an impact on its accuracy for sure.
And for me, did you just say the Reynolds number?
Yeah, the Reynolds number.
That's my last name. I'll remember that forever now.
Any other questions?
One sec.
Is one more accurate than the other, whether you do a 2-point read or a single, or?
Great question. So on most applications, they are the same. The only time we would go to a single path is if it affects the amount of time we need to get the transducer from one side to the other. So what I mean by that is, say we have a very light liquid or a fluid like a gas, then typically having a single path across will be a very short duration, and we won't have the resolution to go directly across. If we have something heavier, like I don't know, water with some solids in it, then we could mount that and really tighten up how much space we need to install one of these units. So that picture I showed earlier, that City of New West application, we could actually mount the transducer on the same section of pipe, but the restrictions around trying to put the transducer to the other side of the pipe and trying to line it up was actually kind of prohibitive. So we ended up mounting it across 2 sections of pipe over like a joint, and that was just easier from an installation standpoint. So it's really down to like what can we actually do and how does the sizing look between the two. But most of the time I've seen a 2-path is the most common. But great question.
Here we go.
Actually, it reminds me of that Victolic clamp that you're talking about with the 2
Yes.
sensors, New West. Does that gap or that joint affect the accuracy, or does it have to be entered into the software, or is that just considered a straight pipe and it's not negligible, the impact on it?
Yeah, I would say that's pretty negligible. What we would want to just make sure is that the bounce doesn't happen right on the joint itself. But yeah, no, that's a great point. Yeah, we would just make sure that we're not hitting that joint at that location. Awesome, thank you.
Any other questions? Nothing online?
Nope. No more online.
Okay. Well, thank you, Jonathan. That was a great presentation.
Thank you.